This assignment is going to help you big time to execute your long essay, your thesis, your project, your dissertation, whichever way you call it. You're going to develop a predictive machine learning model that can be used to forecast the intention of people wearing a mask. That is a target variable. It's been already coded as between 0 and 100. You have some features that influence this intention of people wearing a mask. And some of the features are this and that and this. There are quite a number of them. So you have all of those features there. These features are actually in an Excel or CSV file, which has also been given to you. So you have these features along with, oh, my computer is frozen. Is my screen showing?
Yes, sir. Your screen was showing. But it's off now.
Yeah, because I wasn't getting anybody replying me.
Sorry.
So you have the features such as household income. That will affect the determination to wear masks or not. The year you were born, the coronavirus concern, religiosity, coronavirus intention to stay 6 feet away from people, coronavirus intention to stay home, coronavirus intention to wash your hands, your level of education, that is a dummy variable. College, diploma, graduate, high school, postgraduate. Your gender. It's possible that maybe female are more willing to wear masks than male. And you can see that with gender, there is an other. So the gender is not just male and female, there is other. So take note. Ethnicity, whether the person is Asian, Black, Hispanic, Latino, other mixed race, and white. This is a global thing. No? Religion, whether the person is agnostic, atheist, Buddhist, Catholic, evangelical, Protestant, Hindu, Jewish, Mormon, Muslim, nothing in particular, Orthodox, other Protestant, something else. The employment status of the person, whether the person is a full-time, retired, self-employed, unemployed. So those are the factors. Okay. Now, one of the things you're going to do is, I said there are some things I will edit here. You'll be asked to import some packages, but there are some packages you're supposed to import them yourself. And you're supposed to answer all of these questions as and when they come. Question 1, question 2, question 3, 14, 16, 17, 19, 23. And like I said, I haven't completed. You have about 30 questions to address. That's it. Okay. So whatever we are doing today will help you to address this assignment. And whatever you do go through the assignment with should help you to also handle your exams. Ladies and gentlemen, we are ready now to begin the lecture for today, unless you have a question on the assignment. Okay. So the last time we were able to generate this result, and then we went through in answering some questions. This is the quality wine data set. The wine data set. Like I said, you should have a book and a pen. Some of you say that, oh, I'll watch the video again. Trust me, sometimes watching the video, you will not get much information than now, because now if you listen more, you'll be able to ask questions and then get them addressed. So we're able to go through this. We explain all the elements of the coefficient, the statistics, the R squared, adjusted R squared, the p-value, the F statistics, standard errors. We did all. We analyzed multicollinearity. And then we looked at the theoretical underpinnings of the lasso regression, which in your thesis, when you're writing your thesis, it's important that you bring these models. So if you are estimating the lasso, bring the mathematical model for the lasso, just as I brought here. Do the same thing. Do the same thing. Okay. And then if you have to bring the mathematical formula for the ridge regression, do the same thing. Let your examiner know that you know the model. Don't just write any machine learning model without writing the model. Put the model down. Okay. And OLS regression is the baseline. And the last time I walked you through the OLS regression, this is the OLS regression, the baseline. This is a residual sum of squared that estimates the parameters. You don't understand, you ask. You don't understand, you ask. And it's supposed to know the model and put the model down. Now, for your specific variables, there are many. Some of you have got many variables. So you may have to use summation, just as you see here, where J is from 1 to P, where P is a total number of features. And each of the Xij is one of the features. In our case, each of the Xij represents one of the features here. So for example, fixed acidity for the wine, volatile acidity. All of these are examples of the Xij. So this is how you got to proceed with this very example. We've gone through all of these already. Today, what we are going to do is tantamount to what most of you are doing in journal papers, in theses, and in dissertations. So please pay attention, and then you can now ask questions as we move forward. So I've already given you the lasso and the ridge regression. And I quite remember that we also went through the elastic net, which introduces two penalties, the L1 regularization parameter penalty, and then the L2 regularization parameter penalty. So we worked on that. And this is the elastic net model that minimizes both the lasso with its regularization penalty. And by the way, the first part is the regression, is the OLS regression, this part. And then this part here is the lasso, and then this part here is the ridge. So you have all of these things there. Okay. Now, this part, I'll expect you to read them on yourself. Okay. And it's the same thing when you have to do the same thing for logistic regression. If you have to do logistic regression, if you have to do random forest, if you have to do AdaBoost, CatBoost, lightgbm, xgbm, any of the gradient boosting methods, if you have to do support vector regression, and I'm saying regression because we are looking at continuous variable, not binary. We are not looking at binary classification. But if you are doing binary classification, support vector machine, you can use it for regression. Support vector classifier, you can use it for binary classifications. The same thing, random forest, you can use it for regression. Then the same random forest, you can use it for classification. So you can have random forest regressor, random forest classifier. So take note of these, okay? Any of the decision trees. So you have decision tree classifier, decision tree regressor. So you can use all of these for all of them. Okay, so keep that in mind. And if you're writing any journal paper, you're going to take the angle I'm about to show you. Even if it's a thesis or a journal paper, you're going to follow this. First of all, I've given you a couple of, for this very example we did, you have this journal paper to look at, okay, to just guide you. All right. So apart from the linear regression model, there are other regressions, robust. The Huber regression and the Ransack are very powerful. very robust to outliers, extreme values. So if there's a tendency of outliers and extreme values, that's it. The partial least squares, the least, the quantile, the generalized, the Bayesian, all of them are there, but they are all kind of sort of regression related models. Okay, regression are just, they are still four. They don't have their binary classification versions. They are all for regression, for regression, for regression. For example, we don't have partial least square classifier. No, no. We don't have least angle regression, least angle classifier. No. Quantile classifier. No. Generalized least linear model. No, no. We don't have it for classifications. Okay. So that's it for those ones that are for continuous variables. But then when you're dealing with the decision trees, you can use several methods that can also be used for both classification and for regression. So I'm going to start by reloading the entire data set. So let's say that you want to, and I want you to come home and look at this principle that we're going to do. So this is how your exam is going to be. This is how your assignment is also going to be. We are bringing everything to captivity here right now. We have a data set, and this is a data set which is one data set. On the far right is quality. Quality is the dependent variable, which in machine learning, we call it the target variable. Now, the target variable is a continuous variable. So this is not a binary classification approach. So for those of you who are doing chain, fraud detection, chain, what's the name of those people who do chain? It's a chain prediction, right? And then some of you do loan prediction, gold price prediction. No, gold price prediction is just like what we are doing here. You're not classifying them. Gold price prediction is not a binary, discrete variable. But where you have loan prediction, you have what do you call it? Fraud detection. You have disease detection or prediction. Give me some of the binary classification practicals that you tend to do. Eves, you can't use the Tobit and the Probit. You can't use it. They are designed. First of all, the logistic itself is not, technically speaking, a machine learning model. It's a statistical model. It's an econometric model. It's the baseline. So normally you can't do that alone. You have to, if you are a data scientist, you have to juxtapose that logistic regression, the logit model, together with other machine learning model, because it's not technically a machine learning model. So Tobit, Probit, censored, truncated, all of them are dependent variable regression in the world of econometrics. They are statistical. They are not machine learning. I hope that answers your question. They are statistical. Okay. They all carry some ideas. Some of them will indicate that the values are supposed to be between 0 and 1. Some of them will say that most of the values are 1, few are 0. Oh, okay. So now we are in the world of truncated regression. Some of them will say that there's between 0 and 1, but 0 is not inclusive. 1 is also not inclusive. Some of them will say that it's between 0 and 1, but 0 is inclusive. 1 is also inclusive. Some of them are a whole of, that's what leads to the different Probit, different Tobit. Some of them will even tell you it's just 0 and 1. It's not between 0 and 1, but it's rather 0 and 1 alone. So all of them are econometric models. Okay? They are statistical models and not necessarily machine learning. But then you can use them and top it up. That's it. You can use them and top it up with a machine learning model and check them, cross-validate them to see whether they are good. So I want you all to look at your data set you have. And for those of you who are doing binary classification, can you tell me some of the things you are predicting that are binary? You just want to, I've mentioned loan default, credit rating. What's the name of that? Loan default, credit rating, fraud detection. What else? Can some of you give me some of them? I want practicality. I don't want to be talking alone. I don't want to be hearing myself alone. Trend prediction. Distress. What do you say distress? You have to be clear because distress, are you sure you're looking at? So distress, okay, distress. Whether a company has gone into distress or not. Is that it?
Yes, please.
Okay, so that's a binary classification. Anyone else? Fake news prediction. That is whether the news is fake or the news is not fake. Okay, I love that. What else? Spam prediction. Whether an email is a spam or it's not a spam. What else? Say some. The fact that you can say some here means that you've done something in machine learning. Otherwise, you finish your machine learning course and then you realize that, what did I even do? What did I even do? Yeah, product purchase, buy or not buy, contract, accept or not accept, child weight at birth, low or normal weight. Very good. What else? What else? You are just listening. You want people to mention it. You are not thinking and mentioning some to showcase that you are giving. There's more happiness in giving than in receiving. You are receiving. You've been receiving since you joined the class, since 1910. Now is the time for you to give. Arrears pay or will not pay. I don't understand that. Medical test, negative or positive. Very good. That is a very good outcome. Project risks, to invest or not to invest. Very good. Say some. Do survive or dead. What is survive or dead? You got to be very precise. What is survive or dead? You got to be very clear what you mean by survive or dead. And please also think about the possibility of getting data on some of these things. Because you can mention certain things when there is no way to get data. All right. So those are binary classifications, and we are not looking at them. I'll flag them as we go. What we are looking at are continuous variable. Okay. So these are continuous variables. And we have wine quality as our data set. This is the target variable, and it is affected by the acidity, the fixed acidity, the volatile acidity, the citric acid, the residual sugar, the chloride, the free sulfur dioxide, the total sulfur dioxide of the wine, the density of the wine, the pH of the wine, the sulfates, and the alcohol content of the wine. All of these will affect the wine quality. This is a continuous variable. Okay, so the first thing you got to do, and what I'm showing you is the same thing you do in your thesis. Normally, you look at the models you're going to build as too big, but I want you to look at the models as boom. So the code I'm giving you is a boom code. It's a code that can run multiple models at the same time. I'll demonstrate that here. So first you import your basic libraries, NumPy, Pandas, we know what they are. One is basically for, dealing with matrices and vectors. The other is basically dealing with tables and data frames. Then scikit-learn, everything that is within scikit-learn. Because we are going to look at linear model, range, lasso, elastic net, and Huber regression, which is very good for outlier detection. So we load them. And you will see that in a different code that I'll show you very soon, we will not load only these ones. We will load other ones than these. Along the line, we will also calculate something we call evaluation matrix. Write it down. Evaluation matrix. Write it down. Performance matrix. This is a research question that you should all have. All of you should have a research question where you are able to determine the efficiency of the model. So after you predicted the model, you want to know which of the model is the best or the most efficient. And you use something we call performance metrics or evaluation metrics. There are a number of them when you are dealing with classification models, but we are not looking at classification. For example, if you are dealing with classification models, you have to look at things like the confusion matrix. Okay, the false positive, the false negative, the true positive, the true negative. Then from that, you find your recall, you find your F1 score, you find your ROC, the area under the curve, AUC, and then you'll be able to come out with a judgment to determine whether your model is good. Now, that is for classification. That's for classification. Write it down. Write it down. Write it down. You forget. You forget. But when you're looking at continuous variables like we are doing here, then these performance metrics, these performance indices, this evaluation metrics, they include things like the mean squared error, MSE, MAE, root MSE. Okay? You have the median absolute error, MED, NEDE, AE. Okay? Then the max error, then the MAPE. Sometimes you even have the SMAPE. And then you have your R score, the R square, and then adjusted R square. Okay? And then the VEVS, which is explained variance error. There are quite a number of them, but these are the basic ones, the necessary ones that we tend to use. In the next one, I'll give you more. Okay, so you got to command scikit-learn to give you all of these metrics. Okay, they are called metrics. Then the next thing is to initialize the model so that you don't need to go and run for each model. So you create the model initialization. You tell Python that I want to actually run for OLS. So you put the linear regression model in here. Remember, you have imported all of them from scikit-learn already. And they are all linear, as you can see. So you see that they are all linear, so I didn't include the non-linear ones. Then you would start with the OLS, which is a basic. You include the range, the lasso, the elastic net, the Huber. Okay. Now, as you know, the range, the lasso, and the elastic net, they have what? Regularization parameters. Okay, the alphas, and then the L1 and L2 ratio. So all of them have also been defined there. You can change it. Changing these ones, these numbers is what we call hyperparameter tuning. Changing some of these numbers from 0.1 to 0.9 or to 0.6, these are the alpha parameter tuning. And you can change some of them along the line when you feel they should. But you got to get the intuition behind that tuning before you do it. Then we also import from the same scikit-learn, we import the train test split. We use this thing to split the data into the 80-20 rule, so that we can hold some of the data for testing, okay, in case the models are applied on unseen data. I've used example of writing an exam compared to the test or mock exam. Okay, so the mock exam is like the training, and then the actual exam is like the testing. Then you also have to scale the data if the need arises. Some of this data are too big, some are in millions, some are in zeros. So you have to bring them all into the same scale. So you have to import the standard scaler to do the job. Okay, and here you have to check whether you're going to use the normalization, the standardized one, or you're going to use the minimax, depending on what you're doing. But the standard scaler is the common one we are going to use. Okay, with all that ready, you can now set up your dependent variable and your independent variable. You can set up your features, which is your independent variable, and you can set up your dependent variable, which is a target. So here, watch this carefully. You don't need to type all of them like we did for the OLS last time. You can indicate that I want you to let X represent anything in my data set. The data set is DF. In case you forgot, when you go up here, you can see that I called it DF here. Okay. And then I ran it. I showed just the top part of the data. But of course, you can show just the 20, the first 20, let's say 10 of the data set. Okay. And that gives you just the 10 of the data set. All right. So the data is called DF. So you indicate that I want all the independent variables, I want them to be represented by X matrix. So anything else that is not the dependent variable, anything that is not a feature, is the quality. Quality is the only variable that is the target, which is this. And when you come here, is the one on the far right. Okay, the far right of the table. So that is a feature. So anything, that's a target. So anything that is not a target, you should put it all together into a matrix and call it X. That is what this command does. So it is dropping. That drop means that it is removing anything that is not, quality. It's dropping quality from the X matrix. And then the Y is actually the quality itself. The quality data is found in the DF data frame. The quality variable is obtained from the DF data frame. So you define your factor. You are not going to do this one by one. You're just writing the code. So when you finish, you execute it once. Everything will be done. But you just need to know what is happening. The next thing is that we got to assume, before you do the next command I'm about to show you, you got to assume that you've done the first one that I did here. So once you've done this loading, you've indicated which ones are the features and which ones. In fact, here you can just put a hash symbol and say that to represent, this should represent, okay, the features in the data set. Whereas you can say that this one, indicates the targets. The target is usually 1. And in this case, it's continuous. But if you were doing a binary classification, it is binary. The next thing is to now split the data set. And this command does the job easily. So xtrain, and please note that the splitting of the data set, you are splitting the data set on both the target as well as the features. So xtrain is going to be all these. Look, you can pick out this one alone and you see. So it's going to, the test size is here. The test size is 20%, which means that you are indicating that 20% of the data should represent the test, which means 80% of the data is representing the training data set. So out of either the test or the training, you will have the X variable representing the features, and then you have the Y variable representing the target. So you can see that for the training, we have X train and Y train. And for the test data set, we have the X test and then the Y test. Wherever you see the test, that is 20% of the data, and wherever you see the train, it is 80% of the data. This package here will actually do the splitting of the data according to the way you specify. I'm not going to run that now, okay? It's a kind of data pre-processing activity. The next thing is to standard scale the splitting you have done. So you've done the splitting, Keke. But you've just done it, you indicated that let's put 20% aside, let's go and work with the 80%. So you put a 20% aside. Now let's deal with the 80%. So you can see that every command you are going to see here is not about the 20%. Okay. In fact, you can do for the 20%, but that is not what you're going to use to run your model. Okay. We can do for the testing, as you can see I've done here, but you're only doing this thing because you have a huge code that you're going to run for the testing as well. That's why I'm doing it. But then the initial fitting of the data, if you check it carefully, if you check the fitting of the data, is mainly based on the training set or the train set. So this is going to scale the data for you. We'll show the results now. The next thing is to now do the actual training. Okay. So this very model fitness will train the data set. Okay. So you train the entire data set. And of course, after you've trained the data set, you'll come out with the residuals. And the residuals are obtained from the predicted value. The predicted value is the target value. So in this case, if Q is 1 quality, you have Q cap. Q cap is the predicted wine quality. And the difference between the Q and the Q cap is equal to the error or the residual. This error or the residual, okay, is what you are going to minimize, okay, using an optimization. And then based on the minimization, you can now use it to predict. So eventually, whatever you get here, the Q cap, that is your predicted variable. Any difference between the predicted quality, the wine quality, the predicted variable, and the actual variable, anything between the two is what we call the bias or the loss or the error. So the thing is going to do all of that. The next code that you're going to see, so you can see that I'm giving a couple of instructions here to help in case the person doesn't understand. For example, predictions are made on the test data. They are not made on the trained data. The model will evaluate the performance on the test data alone, not on the training. That's what I said, that you train the model on the training set, and then you come and test it on the test or validate it on the test set. All the metrics you're going to see, the R squared, that means all of them are going to be calculated using the test set. Because the test set will indicate whether your training was good. It's like if I give you mock exams, 3 different mock exams, you get 80%, 90%, and then 95%. It kind of predisposes the fact that you are likely to do well in the actual exam. So when I bring the actual exam, that actual exam is the one we are going to find your GPA on, not on the mock exams you wrote. So these evaluation metrics are like your GPA scores for, or your grade scores for each of the exams you've written. And this is the final exam, not the mock exams that you wrote. Also, you will note that it's indicated here that the X test scaled and the Y test are explicitly used in all the metric calculations. We've said that already. The code does not evaluate performance on the training. We've also said that already. So evaluation is not done on the training set, it's done on the test set. Now, there was no R square. If you check it, when I was importing, okay, I imported mean squared error. I even imported R square score, but I did not import the adjusted R square. So I write a code to indicate the calculation of the adjusted R square. And this code is that. And this is actually a beautiful code for the adjusted R square. Now, having gotten the calculation value for the adjusted, having gotten the code for the adjusted R square, I will now add it to the evaluation matrices. So now you see you have R square, you have adjusted R square, renaming them beautifully. Now I've gotten all, I even have brought the root mean squared error. And check carefully, the root mean squared error has been calculated. It's been calculated. So watch it. It's a mean squared error. Watch it. It's the square root. So I have to bring the square root here. So I'm adding the formula to it automatically. It's the square root of the one above it, the mean squared error, from the test set, okay, using the predicted value. All right. And all of these are following. The next thing is that you command the result to give you the coefficient. So out of all the models that we are doing here, remember the models, there are 5 of them. All of this, you want to give you the coefficient of the model. We're not interested in the standard error, the t statistic, the p-value, the confidence interval, all of those things that we do in the econometric regressions. The key point is that we want the coefficient. That's what we want. Whether the coefficients are significant or they are not significant, we'll find out later using a new approach in machine learning. Okay. And here, we want the coefficient. Apart from that, we also want to know which model is the best based on the R square. Please remember, it's based on the R square. So we are going to create the R square in a descending order. Okay. And of course, there will also be other evaluation matrices like the MEE, the MSE, the root MSE, and all of that. But then the R square is the one that will indicate the descension. So the descending order of the things will be based on the R square. Okay. And so that will be shown in the results. So there will be a kind of a data frame that will be created, and it will sort them out based on the R square. Of course, if you want to change them from the R square sorting, all you got to do is come and remove the word R square here, or remove the word R square, replace it with MSE, if that's what you want. If you want that, to come and replace it with MSE, and everything will be sorted based on the MSE. If you want to replace it with root mean square, you can use that one too. So these ones are changeable. And here, if you check the T, I've indicated that the data frame should be transposed, okay, so that they are in a beautiful vertical order. So you can create a coefficient with the data frame, and then you can create them in that. You can create the R square in the descending order. This final bit will indicate the scores. So we want to display the scores, okay, and one of the scores is going to have model performance metrics. Sometimes, but it's nice to even have evaluation metrics. You can use the word evaluation matrix, and it will be sorted by the R square. And you all have the code, so I want you to do this. So I'm going to run this. Okay. It's running, it's done, depending on the speed of your computer, and now we can see the results. So in this result, look at it very carefully. Everything has been done in the order, descending order of the R square. Okay. So based on this model evaluation sorted by the R square, which of these 5 models would you say is the best model compared to the others? Which of them? Based on the R square. Based on the R square. Which model? We have RAGE, OLS, Huber, and all of that. Okay. Based on the R square, it's RAGE. Now, based on the MAE, based on the mean absolute error, which model is the best? Based on the what do you call it? MAE, which model is the best?
Rich.
It's not RAGE. See, life is not a straight line. And don't do lotto. Understand it. It's not RAGE. These are the things you discuss in your report. It's Huber. Exactly. Somewhere. Okay. If you check it, Huber is the smallest one. It's 5908. So based on the MAE, Huber is the best model. After that, before you go to the what? You go to the RAGE. So you got to understand some things. Life is not always a straight line. Okay. Now, based on the RMSE, oh, no, forget that. Based on the mapping, based on the mapping, okay, minimum absolute percentage error, which model is the best? Based on the mapping. Based on the mapping, it's Huber. Very good. It's Huber. Okay, so you got to be very careful. But we have organized this thing based on the R square. And what do you do? In your tests, in your exams, you're going to have something similar like that. That's what you're going to have. Okay? In your exams, you're going to have something similar like that. Sorry, not in your exams. Yes, in your exam, you're going to have something similar like that. But in your long essays, you're supposed to also note that you will have that principle of coming out with, some of these in your results. Of course, don't take the results in that like that, just design it a little bit. The way I have it here, it is not probably in a beautiful tabular form. So you may have to, have it in a nice tabular form. And then based on that nice tabular way, you can come out with very distinguished result. But the key point, for example, if you look at mine, it didn't continue. You see, It went all the way from R squared, got to MAE, and then it came down and continued from the median. Okay. So in a proper way, it will probably, this latter part, will have to continue to go and join this part here so that you can have a very beautiful result. So that's why I'm saying that you may have to export it. Okay. And you can export everything to Excel and design it nicely. And please remember, whenever you are designing the heading should be at the top. 2 lines should cover the first heading. And then this very part here, there should be another line so that it is well organized. Well organized. Take note. Okay, so we've been able to just determine which model is the best. Keep that in mind. Rage and Huber. Keep in your mind. Rage and Huber. Put it in your mind. Rage and Huber. Okay. The next thing is the coefficient. And I want you to take note of something very important. The coefficient we are finding here, okay, they are not too significantly different from the coefficient we found when we're doing the regression using the R using the R software integration. I quite remember I told you that you can design the results using the R square integration. And that's it. That's what we did there. Now, so look at the OLS. The result is there. Look at the range. The coefficient is there. Okay. Now, based on these coefficients, and I'm asking you a very general question, which variable do you think is the most significant variable among all the features in determining or in predicting quality of wine? Which variable is the most significant in determining or predicting the quality of wine? Your colleagues there who are not on this call, tell them to be on this call. It's going to be a big miss for those that toy with this. Huge miss. Which variable? Eves says density. Oh, I am talking about based on rage. Based on rage. I mean, it's because you mentioned OLS. I just want to say, because we know the best model is rage based on the R square. So now we selected rage as the best. Any possible next one will be the Huber. Okay. So based on rage, which variable is the best in determining the quality? See, some people are saying density, some people are saying citric acid. We'll see. Which variable? It's quite strange the way some of you are getting answers. I say based on the rate result, and the answers I'm getting are not good. Which variable is the most, or is the most important? Even though this is not a better way to determine importance. Which variable? You are wrong, so you have to correct it.
But, sir.
Yes.
But do you have enough information to determine that?
What information would you need? I told you that based on what we have here right now. If there are other information, I'll give you as we go. And yes, okay, based on what we have here, we have something to determine that.
Okay.
We have something to determine which variable, is likely to determine, wine quality based on your data set you have. Okay, so I'm getting strange answers. I'm getting citric acid, I'm getting residual sugar, I'm getting fixed acidity, I'm getting density. Like everybody is mentioning something. Okay. So what you are going to look at first is you're going to look at this variable here. Okay, because that's the biggest in absolute terms. And then you're going to look at that variable. Okay. That is the biggest in positive terms, and the one I circled before is the biggest in negative terms. Okay. So, question is that if you are looking for the variable that positively increase the quality of wine, it is residual sugar. Okay, it is a one that positively, highly, affect residual sugar, affect the quality of wine. If you don't understand, you can raise your hand, we explain it to you. It's a one that greatly influences. But in a negative terms, is density. Density will reduce the quality of, so if the density is high, the quality is reduced. And it is reduced by a huge margin. It's reduced by a huge margin. So take note of how these factors, and keep those two factors in mind because they will show up when we come to the proper evaluation metrics. Okay? When we start using the Shapley additive explanation, which is a very beautiful artificial intelligence, explainable artificial intelligence way of speaking to managers. This variable, density, and that variable, residual sugar, are critical factors, critical predictors in determining the quality of wine. If you don't understand, you ask. Okay. Now, let's go to the next thing. So this is what you do for that. But then some of you in your long essays and in your thesis, you will not even use any of these models. Okay? You will not use any of these models. So we're going to run another model. And in this second model, you will notice that I have included more variables or more models, machine learning models, supervised machine learning models. Supervised machine learning models. And I've included support vector regression. Yes, Amanda.
Doc, please, I'm trying to follow with the code you sent in the group, but it's a bit different from what you're showing.
Which one is a bit different? You mean my results or the code?
No, the codes you put in the group, the codes you gave us in the group, it runs it all the way to the visualizations.
The one I just put there today.
Yes.
You're talking about this one that we ran, this very one?
Yes, it doesn't end here. It goes all the way down, so the results are a bit different.
No problem. No problem. I've given you the other one, so you can check. If
Please,
what
which
you
other
have is
one?
different, I've just given you the one I have here.
Okay, thank you.
So what you do now is that you go to the next one, and the reason I've not taught you support vector regression. Have you guys learned it anywhere with any of the other lectures? No? All right. It's a beautiful, beautiful approach. Okay. But I can't teach you. I'm just telling you how easy it is to run all your models together. Sometimes when some of you are, there was a guy, one of my students I'm supervising, I said that she's going to run 15 models. He said, you don't need to do because these models are here. Already look at how many models you've done. Regression is 1, Rage is 2, Lasso is 3, Elastic Net is 4, EBA is 5. Now we are talking about support vector regression. It's 6, decision trees is 7, random forest is 8, xgboost, extreme gradient boosting regressor is 9. Okay, lightgbm is 10. Okay, multiple layer perception. See, all of them, these are just 11. Okay, once we include 2 more or so, the work is done. And that is how it works. 1 second. The next thing is that after you've done the model, so we've just added some few models. And let me send you this new model before you say that this one too is different. Because, and by the way, if you are following this thing, this is the same way you're going to run your thesis. So you shouldn't worry your supervisors that show me, teach me, show me, teach me. This is it. This is it. You just have to edit some few things if you're doing different models. Now the train test splits and then the standard scaling is all here as always. Okay. So they are here. And then the evaluation matrices are here as always. So preparing the data is the same thing. Testing, creating the test splits, standard scaling, all of them as always is all there like this. The models, and the only thing that is changed is the models. And you can see that now the models are more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I've included even neural network for the multiple layer perception regressor. So you have it all. The only key point to understand is taking your time to understand each of the green numbers for each of them, because some of them are using simulations, some of them are using verbosities, some of them are using iterations, some of them are using different penalty functions, regularization, parameter functions, and all of them. That's what you need to understand. And sometimes you can just pick on some of these code and just put it into DeepSeek or chat or something to get explanations on them. Okay. Once you've created the models, the next thing is to apply the training and the testing and then the evaluation, everything. As always, our adjusted R-square is not there, so we write it and then we rename all of the codes as usual. After that, look here carefully, because this is a very beautiful information here. It was a bit difficult to get coefficients for these decision trees. Did I include decision trees? I think I did. For all the tree-based models, okay, it was difficult to get coefficients for them. Oh, and yes, there are some of the things that you have to install before you start. And if you have not installed them, it will give you an error, okay, and tell you that you have to install them. And I'll mention some of them as you go. For example, if you have not installed certain things that are here, for example, as you can see, I'm saying you should import this, import that, import this, import that. If you are importing, but you have not installed, for example, you've not installed sklearn, you have not installed, sharp, okay, shapely additive explanation, this one, okay, you have to install before you import. So there are certain things that you got to install before you import. And when you make that error, you will be told that this is not found. And when it is not found, you just use pip install to do your pip install. Bring an exclamation mark and just do your pip install. All right. Now, so you write the adjusted R-square formula and you extract the coefficient. So if you check carefully, I'm extracting the coefficient for the OLS, for the lasso, for the range, for elastic, these are all the linear models. I'm extracting it. But when it comes to the tree-based models, I'm not using the coefficient. Take note. Okay. It's either going to be coefficient or feature important, because the tree-based models don't give coefficients. So tree-based models like decision tree, random forest, xgboost, lightgbm, they will rather give you the feature importance. So if you tell it to give you the coefficient, it will say none, 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 because it doesn't provide that. And when it comes to the neural networks, okay, it uses weight from the first layer. Okay, the weights here are again the coefficient. The weight is talking about the importance attached to that particular feature. How important is citric acidity? How important is density? How important is pH? The importance, the weight attached to them. That's what this one gives. And finally, the support vector. That one is for nonlinear kernels. Okay, so that one I used the shapely additive explanation. The shapely additive explanation is a very powerful, explainable artificial intelligence way of interpreting features. It is not the only one. There is also the line, okay? There is a BGP, and there are other ones that you can use to tell the importance. It's beautiful because it comes with beautiful graphs, and you're going to see that very soon. So I put all of this together. I show the result not in a, I sort the values by the R square in an ascending order, in a descending order. So ascending order here will be false. And then in the display section, we display the model performance metrics. Again, I can change it to evaluation metrics, sorted by the R square, then the coefficient, and then I didn't want to do the sorting by each model. I just decided that once it is identify the best model, so tell me the best model. Once you know which model is the best, then use the R square of that best model, because right now I don't know which model is going to be the best. I use the R square of that best model to rank the models. Okay. And then just tell me the result based on the R square, the score of the R square. I want you to rank which variable is the best variable, which feature is the most important feature. Okay? I want the color to be sky blue, okay? Or let's make it blue. And then I want you to add the names. So you see here, add the, because when you submit this in a thesis, it's beautiful in a journal. I want you to add the names on top of each of the bars for the based on the R square. Okay. Add the names, add the number, the R square value. So if the R square value is 50%, just put those ones for that. And then do what? And then plot the graph for me. Finally, for the Shapley additive explanation for the feature importance, pick the best model once again. But I don't know which model is the best, okay? If it is this, if it is based on random forest or xgboost, pick the best from that and use it to draw the Shapley additive explanation graph. Okay. And that is what this one is going to do. Also, don't just draw the graph, get the absolute mean value for each feature, and then create feature importance for each of the features. Okay. And then call it shape value in the descending order. In fact, even plot the importance and label it as shape value, average impact on model output magnitude. Okay. And then again, this one to add the numbers, the feature importance on the bars, just as you did for the R square, for the linear ones. And finally, plot all of this and put it together. This will take some time, okay? I'm going to run it. It will take like 3 minutes, depending on the speed. Of course, the star says that it's running. Okay? If you have been using your computer a lot, like I've been using my computer, you got to give it some time. And we are dealing with data sets, which is, I think, over 4,000 as well. So you got to give it some time. Now, while that is going on, anybody with a question, please ask. So in your long essay, in your thesis, in your journal paper, this is what you will do. Yes, Marilyn.
Thank you, Prof. Doc, sorry. Please, I wanted to find out for our thesis, are we to try everything like this, or we need to select one and use it?
Everything, my dear.
Okay.
Try everything. It's the best.
Yes, sir.
It's the best. You give whoever is looking at your paper as you've explored all avenues before coming out with. And you won't die, and it's not hard because the same thing is going to be run at the same time anyway. You see, I've done 11 models. Okay. I've done 11 different models put together. It's running. It's running. It takes some bit of time, 3 to 5 minutes or so, it will run.
But Prof, I have a question, please.
Who's talking? I can't see
so
that.
as a follow-up to her question.
Who is talking? Who is talking?
Hello? Hello?
Who is talking? I can't see the person because I'm not watching the thing. I'm opening the, I'm watching my screen. So the person should raise their hand so that I know the person.
Oh, okay, sorry.
Okay.
Okay, so my question was a follow-up to your response. That we should run all the different models. I would have thought that that should depend on what you're studying, because I don't know if all the models will be appropriate, for the kind of studies you're doing.
I'm not so sure that the question she asked is based on the study she's doing. So I don't need to tell her that, oh, that means that if you are running binary classification, go and run all the models that are for non-binary classification. Of course not. But you run the models that are for binary classification. Yes, run all the models for binary classification.
Okay.
But if you are doing for non-binary classification, continuous data variable, like what we are doing, I've run all. Well, I've even finished running all. Okay. Whichever one you run, you see, the thing is that when you don't understand what you are doing, that is when you stick to one thing and you come out with a wrong result. Suppose I have just gone to run regression alone. You just look at the results now, and you will see that if I ran only regression, the first 5 that I did, I would have failed Potol. Meanwhile, there were 5 I did. There were 5 different models I did. But if I had used that, I would have failed Potol. I'll come back to your question. Isaac, your hand is up.
All right, so I put my hand back down. I was struggling to get it to work, but I've been able to run it, and the results are just beautiful. It's impressive that we get the results for all the models in one go like this. So
Yes,
thank
this
you
is
very
what you're
much.
supposed to learn. This is why I'm giving you these things so that you go. Otherwise, you guys are going to be tired and you don't know what to do. And right now, if you do this, your thesis is sorted. If you get this kind of results I'm about to show you, your entire thesis, all your research questions will be answered, like that with the results. For example, now based on this model, based on this result, which model is now the best? Based on the R square, sorted by the R square, which model is the best?
For mine, based on the R squared, random forest was the best, followed by xgboost.
Good. Let's hold on there. Based on the root mean squared error, which model is the best? Root mean squared error. It's still the random forest.
It's still the random forest. That one, the lowest figure is the best.
So, but then you can see that when we use the first one, OLS was good in the R square, but Huber was good in the other one. Do you remember?
Yes, sir.
There was inconsistencies there. So, but you will not fully take the first one all the time. My advice is that you always take the first 3. Because sometimes the others will also be doing well relative to. And again, remember, this is based on your data. This is based on your data. Okay, this is based on. But if somebody should use another data and get the same random forest being the best, then random forest is consistently seen as doing well when it comes to A, B, C, and D. Okay, now, so on all these, you can see that OLS was good at first, but now it's somewhere down here. And what is even interesting is that using this new approach, these new methods, you will notice that even using the R square, the Huber has bypassed the OLS. Do you see that? The Huber has bypassed the OLS. Question you got to ask yourself is why? Because the previous one was the same data set we're using. But why is it that now the Huber has bypassed the OLS? There's an answer in there. So in terms of which model performs the best, you are able to see that, oh, random forest performs the best. But not just that. Now let's come to model coefficient. In the model coefficient, remember that, in fact, I can take each one of them and analyze the model coefficient for each one of them. Do you guys remember which two variables were doing well when we started? Which two variables were doing well? Which two coefficients were doing well? One of them was what? On the positive side, it was residual sugar. Do you remember?
Yes, Prof.
Yes.
On the negative side, it was what?
Density.
Density.
Now, they haven't changed. Okay, so let's go. And I'm talking about the OLS. On the OLS section, they haven't changed. But more importantly, we are dealing with the best model here. And the best model is random forest. So let's look at the random forest. What do you notice? Okay. What do you notice here? When it comes to which model is doing well, you will notice that alcohol is doing the best here. Do you see that? Alcohol.
Yes.
Alcohol is a good indicator, well, appears to be a good indicator of wine quality. Alcohol, which is the next one. And by the way, they are all positive. So that's what they are. Which is the next variable?
Volatile acidity.
Volatile acidity.
Yeah.
Okay. Volatile acidity. So these two, take note of them. Alcohol and volatile. And again, remember, whatever we had before was irrelevant. Because now it's the best model we are focusing on. It's the best modulo tone. That's what we are focusing on. Now, let's go and check the model performance. I had to do a lot of work to be able to come out with these things so that I'll give you these posts. So this is the model performance comparison using the R square. And you will see these things in thesis. Remember, this is it. This is what they do, and then they show you the result. You can see that the graphical work shows which model is doing very well based on the R square. And you can see that it is a random forest, followed by xgboost, followed by lightgbm. In fact, most of the tree-based algorithms are doing very, very well. Okay. And the linear ones are not doing so good in this context. Okay. So the graph just supports what we had before. The next thing is using the Shapley additive explanations. Remember, this is a beautiful work, and I'm telling you, top journals, and I'll show you very soon, top journals have begun using this as a way. In fact, it's something, it's so unique that I recently even got to learn about it, to be honest with you. For example, the paper that I posted to you guys in the group page, this is a first time. By the way, anytime, Frank,
Prof.
can you post the general ranking link to them on the page so that they know?
Prof, please, I'm not in there, but I'll send it to one of my colleagues so that they'll post on their page.
Any of them are here. Your colleagues that I supervise, any of them are here. They can put it there for them. Okay. Because they're listening. I think Joseph or Kwame is here. So,
Kwame, please do so. Kwame. Okay.
So you guys, you should use that ranking. Anytime you are citing a paper, use that ranking quickly and go and check whether the paper is in that ABS general ranking. Otherwise, take your time. Don't be citing papers that are not in highly ranked. By the way, this is a journal from the European Journal of Operational Research. And look at it. This is the same thing they are using. The same thing I just showed you. Okay. They are still using what? The same Shapley additive explanation. See the bottom. What are they calling it? Mean shape value, average impact on model output magnitude. Now, compare that with our own. Okay. The same thing here. Okay. Look at the bottom here. That is the same. So when the journals are relieving things, okay, the same thing, average impact on model output magnitude. But in fact, what we have here is even more beautiful than what they have. Do you see that? Who can tell me why I'm saying that what we have is more beautiful than? Kwame, I meant you should post it in the WhatsApp page, not here. What we have here is more beautiful than what they have there. Who can tell me why? why I'm saying that. Who can guess and tell me why I'm saying? Because it's important. It's important and it's easier. Managers easily understand this than that one, even though they are all good. But that one is not all too beautiful because exactly, Coco, that's your answer I'm looking for. Okay, your answer is the best I'm looking for. It is the fact that the importance are not shown here. The value importance are not shown. But if you look at our own that we just did, we have indicated the code in such a way that the important, remember, these importance are add up to 100%. Shape additive explanation is powerful. Guys, don't, if you start using them, you see that you are now learning. They're powerful. Do you remember I told you that the two variables that might be good are alcohol and volatile acidity? And you can see that truly the importance are being exhibited here. So you are able to quickly, and by the way, one of the things, this one, what makes it good is that it tells you that alcohol is not just the best, but it tells you the percentage of its best. So among all the variables, how many are the variables? 11. 1, 2, 3, 1, 2, 3, 2, 3. Yeah. Among all the variables, the 11 variables, alcohol alone is contributing 34% importance towards the prediction of wine quality. Can you imagine that? So it's not only telling you that alcohol is the best, but it's also telling you the percentage of the best. So these values you are seeing are percentage values, and when they add up exactly to 100%. And alcohol alone is contributing a significant proportion towards the prediction of wine quality, according to the best model. In fact, you can also do according to the next best model to see whether alcohol maintains its lead. You can do the next best model, which is the xgboost. All you got to do is that when you go to the code, change using the best model and then replace it with the next one, and then like that, and then like that, and then like that. And you can do maybe the first 3. And then for each one of them, alcohol might show. In fact, that is what this guy did in the paper. So you can see that he has this first one. And when you go down, okay, he has another way of showcasing, okay, another way of trying to showcase. Then when you go down, he has another way of showing, so you can do the similar one to showcase. So if 4-star journal papers are doing that, how much more you? Don't remove none. Is it advisable to remove non-importance and rerun the model? No, it will still keep that percentage value. If a variable is already non-important, it will bring 0 value. Okay, so it's not because something is non-important. Okay, even if you run, let me give you an example of what I mean. Okay, this one is 33%. Okay, now if a variable is 0, okay, the fact that it's not bringing the 0 doesn't mean that whatever percentage it has is added to the rest. If you remove that variable, it is as though it is there by 0. So there is no need it will mention the variable. That's what I'm saying. If the variable is not important, okay, in fact, in my previous other ones, it will showcase the variable as there, but on the line. It's there, but it's on the line, but nothing. But sometimes you can indicate that I don't want to see those that are not important. And you can simply exclude them, but it doesn't change the values of the other ones. So if chloride is still showing 5.1%, it will still show 5.1%. If pH is showing 5.2%, it will still show 5.2%, even if you remove all the other ones below pH. It will still show that because that is its contribution. Okay, so that is exactly what you will notice. So watch the way you pick. The first thing is to pick the which model is the best. Second is to determine feature importance. Now, let's go to the next thing. There is something here which is using the bee swarm, and it's beautiful. You see, the thing about the bee swarm is that it also does the importance, but it uses the integrity of importance. Okay? This is an advanced level. I'll leave you to go and look at that because that is not really part of the syllabus. But that is a very nice. This is again the one the paper gave us. Okay? This is exactly like the one we did before, but this is the one just like the one in the paper. The paper didn't bring the numbers. So again, it's the same thing, but I brought the numbers for this. In fact, let me show you something. No, it will delay 4 minutes. Otherwise, I was going to show you that you can always change the coloring. You can change the coloring at any time. Now, the next thing. I also decided to run this same model.
Prof, kindly hold on a question.
Yeah.
Please, the Shapley importance, we did the first one, and then there is a second one down there. What is the
one with the
difference?
bee swarm, this one.
After the bee swarm.
Oh, it's the same thing. It's a repetition of the first one.
Oh, okay. I was concerned. Okay, all right. Thank you.
See,
Well
it
noted.
ends at 0.35 at the bottom here.
Yeah.
You go to this one, the same thing. It ends at 0.35 at the bottom.
Okay.
It's the same thing. Just I like this one because this one is giving us, beautiful numbers. The weight are assigned to it.
So we can take the second one out of the code.
Exactly. You can take the second one out of the code.
Okay. Thank you, sir.
Now the next thing is using the same. Yes, Daniel.
Yes, Doc. I just want to find out. Yes, when it comes to the metrics, we use all the metrics: R squared, adjusted, R squared, MSE, and all of that. In essence, would it be a good practice, or is there a way where we have, let's say, superiority of metrics, for instance, so that then I wouldn't need to load all of them for academic purposes? Yes, for us to be able to do comparison and all of that. But do you have superiority when it comes to metrics, so that you
each one is good on
it and select just 2 out of the lot?
Get a lot, and normally they corroborate each other. So just do all of it and just confirm it. You will see that if one of them says that xgboost is the best, majority of them will also confirm. Maybe 1 or 2 will deviate from the normalcy, but majority of them will confirm. So now you know in your heart of heart, when you are reporting the results, you can report only 1 or 2 if you like. But what you have done is that you have done a comparative analysis of evaluation metrics, and you can conclude that, look, I did for all the others, and I got the same result that xgboost, or in this case, random forest was the best. But if you don't do that, and somebody says that you use only R squared, okay, what about the other evaluation metrics? What did they also conclude? Oh, I didn't do that. You didn't do that? Oh, no. Why didn't you do it to just check? Why didn't you just do to just check?
All right, thank you. I get you, Doc.
Yeah.
Doc. So in essence, would it be a no starter to say that adjusted R squared as a metric is better than R squared?
No, not exactly. It is only better than the R squared if the difference is wider. And I'm sure you know what that means. Adjusted is better than the R squared only if the difference between them is wider. Because if the difference between them is wider, it means that there are a lot of irrelevant variables in the model. That is why adjusted is widely done. Other than that, they are the same. In fact, majority of studies don't even talk about adjusted R squared. I just want you to know that
thank you
is the same. And generally 2 is the same. Generally. You check a number of papers, they will hardly talk about that. All right. Now the next one, yes, Amma.
Doc, please, what if there are more categorical independent variables, and then the target variable is on a scale of 1 to 10. Does these models still apply?
But that's what we are doing right now. The target variable is 1 to 10, and there are more categorical variables.
Okay. Thank you, Doc.
It applies.
All right.
Okay, so what we
Thank you.
just did is the same thing we have done here. And you can see that I have brought the R square and adjusted R square even here, okay, in a graph. And by the way, you can put all these graphs also in your work. And just right click here, okay, and then you pick it, what is it? Copy to output. Then you go to your Word document, okay, and then here, you can just paste. You see, everything has been pasted nicely in the Word document. That's it. You can write the title under it. Figure 14. I'm just saying 14 so that you'll be scared. A graph of evaluation matrix. For random forest. Regressor. That's it. But remember, when you're writing a figure name, it should be below. When you're writing a table name, it should be above. And so this figure, I did it in such a way that they are all together instead of separate. So that it becomes, you don't use a lot of space. And then you can see, this is only for the random forest, don't forget. As you can see down here, you can see that the random forest is, by the way, this is a Word document I'm using at this stage. This is a Word document, but let's go back to the original. Yes, Luis.
Yeah, thank you, Doc. Doc, so in the same way, how do we push our formulas to Word?
Formulas to Word?
Yes.
Where did you write the formulas?
Assuming I have some written in the Jupyter notebook and I want to copy it there.
You wrote a mathematical formula in a Jupyter notebook. Why don't you use
Yes.
mass type equation editor? Why don't you use the equation editor in Microsoft Word?
All right. Thank you, Doc.
Yeah, you can do everything there.
Thank you.
In fact, even in my professional journal, I use Microsoft Word, and then I'm sure you know that equation editor I'm talking about.
Yes, Doc.
All right, okay. All right, so these graphs are all confirming. Okay, you can see the random forest is having the highest R square and the highest adjusted R square. In fact, I did this thing multiple times because I wanted the thing to be, at first, the value of the R square and adjusted were jammed together. It wasn't looking beautiful here at all. So I rewrote the code so that the adjusted R square will be removed. So the numbers you see are for the sky blue color. The R square is not for the adjusted R square. Okay, it's just so you know. And by the way, our random forest is leading. When you come to another metric, the root mean squared, the MAE, and then the median AE, all of them you can see again consistently. Oh, by the way, you want the lowest one. And you see, when you draw it like this, it quickly helps you to know which one is the lowest. Okay. And again, you can see that consistently, the random forest is the lowest. Remember, for R square, you want the value to be highest. For the errors, you want the value to be lowest. Okay. And you can see that looking at this section here, random forest is leading in all of them. It's leading in all of them. It's leading in all of them. Okay. It's beautiful. It's beautiful. This is a whole completed work. Now, looking at the mapping, once again, you see the random forest is leading. See, you can put one sentence to talk about all this in your work, but the graph will make the reader enjoy what you have done. What you've done now shows clearly that, wow, I love this. I think one of you, when you run the code, you yourself said, wow, because everything is turning out that random forest is consistently XGBoost, following XG, you're consistently doing well. All right. Then, again, this is, so what I have here is for the models. What about the coefficient? So this one, I decided to take each of the coefficients. This one is not too important because the Shapley additive explanation has done the job already for us. Okay. But this one, again, what it does is that I think I haven't run this code. Yes, Amanda. Yeah, I think I haven't run this code. Yeah, Amanda, go ahead.
Yes, Doc, please, can you go up? I want to get some clarification on the maximum error comparison.
Maximum error comparison.
Yes, a graph.
This one. Is it the one showing?
Yes, the one down.
Mhm.
You said that for the maximum error comparison, the random forest is the one leading, but the
No, I
light,
didn't say the one leading. I said for most of them, the random forest is the one leading. For that one, you can see the light GBM is leading.
okay, you circled that one, so that's why I was.
And I did say also that it might be that for some of them, the one that is leading is not leading in all of them, but is leading in the majority of them. So you are right. In this case, light GBM is the best, but random forest has consistently shown itself, even in the three combined here. Light GBM was still good, but but where you see a situation where light GBM is good, like you have seen, flag that out. It's still a good point to note that, oh, light GBM. It's not even only light GBM. In fact, lasso, look at it. For the maximum error comparison, lasso is doing well than random forest. Lasso, even lasso, which is at the bottom, according to the R-square situation. Lasso is doing well there. But that is on a rare situation. That's how I would see it. Okay. There was a code I was running. What was that code? There was a code I was running to show you guys something. I've forgotten the code. I was running a code for the coefficients. Oh, yeah. And it says that I don't have what? Sn. Okay. So I didn't really have, let me just, I didn't really have that particular code showing. So it's possible that I have an error for that particular code. So what I want to do is I want to just note the possibility of correcting that very code. But again, when you have code issues like that, just go to any of the chats to be able to seek, clarification or something. But
Doc.
Yep.
Hello, Doc.
Yep.
This is Ted. Please, I see that the error is indicating that SNS is not defined.
Yes.
So I think maybe we just have to import C-bonds.
Yeah. C-bond is what I'm trying to import. And then sometimes it's not just the C-bond. Sometimes so when you get this, all you got to do is to just check the error, and then you can now get a better way of correcting it.
Okay.
But that's not what I'm doing. I want us to see whether that is important. I don't know what that code I've written is, to be honest. I'm trying to understand what that code I've written is. Other than that, this is a code. Let's see. I think it's one of the visualization. There you go. Okay. So again, it is for the features. I mean, we've seen a lot about the features. And this one, it talks about each feature and what it's doing. And if you check carefully, it has focused on the ridge. Okay. It has focused on the ridge. So it's using the ridge color to indicate which feature is doing well. It was residual sugar, isn't it? And what? Which one did we had? And density.
Density.
Residual sugar and density. It has swapped here a little bit. Well, but I don't think that this code is let me see. I don't think that this code is a better way to. The good thing is that it will show the rest, but the thing is that because random forest is leading, I'll just delete it. So if you get that code, just delete it. It's not too important. Okay. And this is another way. All of these that I've shown here in the slides, there are other ways to see the importance. That's all. It's just to see the importance. I'm not going to run most of them. It's just to see the importance because I was trying to do a lot of try and errors. But the most important ones is what I've shown you. For example, if you look at this, it repeats the same thing as we have done. And then it shows this one. This one, the good thing about this graph, which I posted in the page, is that it juxtaposes the R square against the root mean squared error. So you can see that the root mean squared error is being measured on the right-hand side. It's another beautiful way of showing the graph. Then the R square is measured on the x-axis. So you can see that, again, random forest is leading. And in terms of error, it is among the lowest errors there. It's among the lowest error because if you match the errors to this, it is towards the 0.6 area. If you check this one. So once again, you see that this is an interesting graph that you can show because most of the time they put all the errors together and separate the errors from the R squares. So most of the time R square is standing on its own. But there's another graph, you see, where you can measure R square relative to the root mean squared error. It's good. So, but again, it leads to the same conclusion. And then as for the B swarm, I've told you, go and study it. It's very important. It's very important. You should use this B swarm in your work. If you are determining feature importance, particularly for, whether it is binary classifiers or regression, any one of them, use this one to do the magic. And again, these are several other means of showing the same thing again and again for the errors and for these other ones. So the most important thing for what we have done today is your ability to be able to determine which model is the best and which feature is the best. Which model is the best, which feature is the best. And then now, you are now going to make recommendations. Okay? The recommendations are that, the tree-based system. See, if we had used a traditional based model of OLS regression, of linear, what this means is that there are some issues about outliers, issues about nonlinearity, issues about complexities in the data that the linear models couldn't handle. But the tree-based models are able to beautifully handle. Okay. And that is why the tree-based, because the random forest is an ensemble technique. And it's able to now ensemble several things and then put the solution out. So comparing these models help to be able to come out with a beautiful conclusion. Your managerial expertise must come in. You got to advise managers, or you got to advise researchers to do model comparisons, algorithm comparisons to be able to come out with the best. And also, now you can make managerial advice on what they should do with density and residual sugar. So you now go back to the literature and then density and residual sugar. Now you now give a bit of advice, a bit of things, what can also increase density, what can also reduce the residual sugar. You now bring some practicalities to your work and boom, you give an advice. Daniel.
Yes, thank you, Doc. I want to pick your thoughts on this. So for some of us with the thesis that we are writing, let me speak to myself. So what I've come to know in building up the process, for instance, you would want to categorize your models so that you have the base models, and then you advance in that until you bring those ones that are in high dimensions and stuff like that, so that it all speaks to what you've just done. Is it a good practice to just lump all of them together like this and then do a write-up of it, or you go in that systematic order? As in, you categorize your base models, you run, and then you move on to the next batch of models in that order.
Oh, no. If you can remember, there was one baseline model I had, and we did it last week. That was the OLS regression, if you could remember. So you run that one separately. If you are doing binary classification, the base model will be logistic regression. You run that one separately and interpret all the scores you've got. Then you now come to the comparison. And the comparison, you don't need to do it additions. You just run all of them at a go. And then you select the best, maybe the 2 best or the 3 best, depending on how you want to go around it. And then you now work with those best that you selected. That's it. You don't need to be, let me add the lasso to it and see. Let me add this one to it and see. You'll be tired. Don't do it. Just run it all at a go and do it the way we've done it.
Thank you, Doc.
All right. Now, how do all of these relate to your thesis? So in your thesis, you should, in your exams, you should be able to understand exploratory data analysis. Okay. You should be able to understand exploratory data analysis. You should be able to understand pre-processing, data pre-processing, outlier detection. So let me repeat. Understand descriptive statistics. Distinguish, when you are given a data set and you have descriptive statistics, you should be able to distinguish, identify some of the variables, their means and their standard deviations, and what the central tendency tells you, how different the values of the dispersion relative to that of the central tendency, what they tell you. That's the first part. Second, while some contingency tables have been provided for you, okay, and we did this thing using some, I think when we were looking at Brook to data set or something, when contingency tables have been given to you, you should be able to know which groups use more of the dependent variable or the target variable, which group is doing more of it. You should be able to know which group is, what is the number of the observations that are atheists, that are Buddhists, that are Christians. Okay. Did I use the quantity demanded data with you guys? I think I did. You should be able to explain kernel density plots, box plots, when they are given to you. You should be able to explain that. You should be able to distinguish between balanced and imbalanced data. Test split, validation split, you should be able to distinguish that. And then you should be able to test if there's a significant difference. Okay. So most of this, you're not going to run the thing. The thing will be run, the results will be given to you, then you interpret. So in a 2 sample case, how do you interpret? In a 3 sample case, how do you interpret the scores? And then we come to the regression. In the regression, suppose a complete regression is given to you. Okay. You should be able to determine which variables are significant using the simple OLS approach. Which variables are significant, which variables are not significant. Whether the variables are jointly significant. How to formulate the regression model. Okay. How to determine the reliability of the model using the R square, how to determine the joint significance using the F test. How to determine the accuracy of them, like given the multiple machine learning models, which one you are able to determine whether it's the best or it's not the best. You should be able to tell. And this will go to everyone. This question I'm certain is for all the groups, not only one group, all the 5 groups. And then how to, based on the model you have selected to be the best, how to determine which feature or which of the top 3 features are, which features are the top 3 based on the model you have selected. Okay. Based on the, let's say that you are selecting the top 2 models. And based on the top 2 models, which features are the best? You will use the graph. You also have the table, so you should be able to know which one you want to use. It's up to you. All of them will give you the same answer. And what to be a managerial implication, 1 sentence managerial implication you can tell managers based on that feature importance. So those are the questions that you are going to be able to address in your exams. Having said that, most of these same things is what you need to do your thesis or your dissertation. Yes, Patience.
Yeah, Doc, good afternoon. I was going to say, I was going to request if you could go over those things again.
You have a recording. You can just play the recording again.
Mostly when you repeat, you add more flesh. That's why.
Add more flesh. I don't add more, I add more flesh. Can somebody start from? I don't know what I said. I've forgotten everything I said.
Prof, you started by saying that when we get the data, we should look at the descriptive.
Well, let me give you an advice. If you are able to go through your assignment, because you are writing this paper in September, right?
Yes.
Good. Your assignment is going to be submitted on the 25th of August.
Mm-hmm.
If you can go through the entire assignment and
the paper is on 30th.
It's good. It's still the same thing. You still have 5 days to complete. After you submitted, you still have 5 days to prepare the assignment. So the preparation of this thing, what I can tell you to give you confidence, if you can do the assignment by the 25th and submit, and you understand what you did as a group, there is no way the exam will beat you. I promise you that. But if you don't understand assignment, that is when you'll have a challenge. Yes, Isaac.
Sir, the submission date for the assignment, could we push it back a bit? Like maybe on the Wednesday or on the Thursday, we'll be writing that paper that week, and we'll focus on preparing for that paper and doing the assignments as well. Whilst we are doing that, we'll be learning. The previous week, we'll be preparing for another paper or other papers. So it will be difficult for us to be working on that one whilst we have other papers that we are going to write exams on in that week. So if we could take it to maybe 28th or 27th, that week we are preparing for these papers, this one and another one. So it's easier for us to work on it. And once we've worked on it and it's fresh in our minds, we are able to better do the exams, if that is okay.
I agree with you, but you know that somebody will rather prepare for the exam and not do the assignment and rather start the assignment from 26 after the exams. So the assignment still didn't help the person.
That would be an outlier. That would be an outlier situation. The general one is what Ike is talking about.
You all agree with what Ike is saying?
100%.
I mean, what you are describing would be the outlier situation.
And I'm saying that do you all agree? Because I'm only hearing your mouth. If you
Yes,
all
Doc.
raise your hand, those of you
Yes,
agree.
we do.
Raise
Yes,
your hand
Doc,
and
we
let me
agree.
see.
We agree, we
Don't
do.
say we, say I agree. And I want to see
We
whether they
agree.
agree with you.
I agree.
Prof, I agree.
I'm only having 6 people. So there's no way that shows that you agree. If you have 54 people and 6 people have raised
Doc,
their hand,
I agree.
don't say you agree, just raise your hand. That is enough. If the number doesn't go with the what I see, the people here, there's no way to actually agree with you. There's no way. You see, some people have just logged in and they are sitting down and they will bring you guys down. If I don't get 80% of people agreeing, I will not be able to accept it. I can imagine that somebody is calling somebody. Unfortunately, the number is not enough. Let me see the number I have.
Doc, then why don't you also ask those who disagree to show by hand?
I want to ask. I have 74%. I didn't get the 80%.
From 74
Doc, that is way
final.
above average.
From 74 is a final.
Average.
Doc, we are whipping others in line.
Way above
Like average. I don't want an imbalance data set. And an imbalance is when you are even having 90%. So if you check, have not raised their hands, contact them to raise their hand. Otherwise, I'm not going to accept. I won't lie to you. I won't lie to you. I'm not going to accept.
So tune the parameter. Very well.
I must say that it's been a joy having everyone during this program. You're about to start your entire exam journey. I wish you all the very best. I also want to believe that what we have learned today should help you write your thesis well. I think it has opened your mind, hasn't it? To be able to have a better way to look at your entire thesis. Because that's what I have in mind. Because I can see that most people are struggling with the thesis. But with this one and going over it again, your thesis should be in clear shape. Because if you do this thing that we've just gone through, I can tell you most of your research questions will be answered by the analysis. And of course, it's not difficult translating this straight away to your binary classifications, even for those of you doing binary classifications. And a few of you are doing stock market analysis. It's the same thing. You know, some of you are using long short-term memory. You are using Prophet. You are using ARIMA, Gamma, Arch, you know, all of those autoregressive integrated moving averages, all of the different forecasting methods. It doesn't matter. It's the same principle. Same principle. So I wish you all the very best in your exams. I wish you all the best in your preparation. Have a wonderful, wonderful month. Enjoy your moment. The day that you will throw your gown, your hat above your head. The day that you will look back and the Egyptian you have seen throughout your journey, you will remember your pain no more. Life is a journey. You are passing through your Red Sea, but guaranteed you will reach your promised land. There will be desert, but guaranteed you will reach your Canaan. So see this as a stepping stone. Whatever is you're going through is making you. It is an end that justifies the means. Make yourself proud and wear your gown chest out, shoulder high, and tell yourself eventually, after some few months, you say, I did it. It was hard. It was difficult. It was torturous. It was hard. But hey, I did it anyway. And you will look back and you tell yourself, I made it. So let that be your stepping moment. And I wish you all the very best. Have a wonderful weekend. Bye-bye.
Thank you.